Kinetic molecular theory is kind of an explanation of the behavior of molecules. So remember that we have talked about the difference between theories and laws. Theory is not like a theory in a TV show where they say, well, my theory of how this crime was committed. It's not the same meaning of the word. A theory in chemistry is an explanation that is them gathering all the information we know now to currently explain the model that we have, in this case, for the behavior of molecules. It used to be just gases, but now it's applied to all three common phases. So kinetic molecular theory is trying to explain the behavior of molecules. Okay, so when we say we're describing the phases of matter, we're talking about the common phases of matter. The common phases of matter are solid, liquid, and gas. You might have heard of some other phases of matter, but that's not necessarily what we're talking about when we're describing kinetic molecular theory. So definite volume. Solids and liquids both have definite volume. Gases, however, fill the container that they're in. So this is the reason why when you walk into my classroom, there's oxygen in all of the different corners of the room. You don't have to worry about finding a spot that has more oxygen than the other. Because of gravity, the atmosphere is a blanket of air over the entire Earth, which serves us very well. Definite shape. Solids have definite shape. Your desk looks exactly the same yesterday, today, tomorrow when you come in. Liquids, however, will change shape depending on the container you put them in, but they'll only fill to a level, whereas gases fill the entire container every time. Potential energy, we're talking about the spacing between the molecules. So potential energy has to do with their position. So this is the energy of position, potential energy is. So in solids, the particles are touching. In liquids, they're still kind of touching, but there's bigger spaces between the particles in liquids. This is why largely for most substances, with the exception of water, the solids are more dense because the particles are closer together. Gases, however, have large spaces between the particles, a lot of empty space in gases. And the types of motions, what that means is when you have a solid, it is locked into a rigid spot, or crystal lattice, a lot of times they'll call it, meaning that the molecules can vibrate and spin, but they are locked into position. When it comes to liquids, it says vibrate, spins, and linear. That means they can slide past each other and they can flow. So liquids and gases are considered fluids, meaning that the particles can flow past each other. Gases have a lot wider range of movement than liquids do, but they can also flow and slide past each other. Kinetic energy is the relative speed of the particles. So even though all molecules are in motion, the motion of solids will be very small and gases will be very fast. When you have a solid of the same substance, the kinetic and potential energy of the solid will be the lowest and the gases will be the highest. Temperature increases. So when you increase the temperature of a substance, the particles are going to be affected. It increases the motion. So temperature is a measure of the kinetic energy, which is the energy of motion. When you have a solid and you increase the temperature of it, the solid will expand a very little bit, not very much. It does expand a little bit. That's why when you see roads and sidewalks, you'll see that they have cracks in them that are specifically put in particular places to try to accommodate for the expansion of solids when the temperature increases. Liquids are not affected by temperature increase very much either. Their expansion is small. Compressible. Compressibility has to do with if you apply pressure to it, will you be able to decrease the volume. So kinetic molecular theory has some assumptions. What that means is we're going to simplify and talk about just a few small parts of the way motion of molecules is affected. So the first assumption of KMT is that all matter is composed of tiny indivisible particles called molecules or atoms. So we've been learning since the beginning, we know that's not true. We know that inside of atoms, we have protons, neutrons, and electrons. But the reason we're going to say this assumption is that once you break them down any further than molecules or atoms, they are no longer the same molecule or atom. Once I start taking electrons away from an atom, I have an ion. It's not an atom anymore. So the first assumption is that matter is composed of tiny indivisible particles. Our second assumption of kinetic molecular theory is going to be that all molecules are in constant motion. So you can see that solids will be moving in place. Liquids will fill their container to a level, but they will be able to flow past each other, whereas gases will fill their containers and they will be moving faster. So you can compare the relative speeds of the different particles based on their state of matter. The third assumption of KMT is that the collisions between molecules are elastic. That means that there's no transfer of energy as they collide, nor is there any heat released during the collision. Now, this is not really possible because every time you have collisions, doesn't matter what's colliding, there is a transfer of energy. But we're going to say the transfer of energy is so small that we're going to ignore it because the effect is negligible, and that makes our model a little easier to understand. Fourth assumption of KMT is that the molecules are not attracted nor repelled from each other. So we learned about polar molecules versus nonpolar molecules, and that polar molecules are attracted to each other more than nonpolar molecules. But in kinetic molecular theory, for our simplification purposes, we're going to ignore the repulsion or attraction between molecules. And the last one, which is the most important to us, is that the average kinetic energy or speed of molecules is related to the temperature, Kelvin, not Celsius. And we'll find out why in a minute. So we said all particles are in motion. When all molecular motion stops, that is a temperature that we're going to call absolute zero. We have not gotten to absolute zero. As a matter of fact, we don't even think we can get to absolute zero. As a matter of fact, it would violate some of the laws of nature. So on this planet, we should not be able to get to absolute zero. So how do we even know what absolute zero is? Well, we've done tons and tons and lots of experiments, and we've extrapolated back to the absolute zero temperature. So let's talk about why we can't have Celsius and Fahrenheit. This is the relationship between Kelvin, Celsius, and Fahrenheit. Degrees Celsius and Kelvin are the same size temperature scale. They're the same size degree, whereas Fahrenheit is a smaller degree. So let's talk about what we do know of Celsius and Fahrenheit. Can anybody guess what is the Celsius temperature outside today? Who's got a good guess for Celsius temperature? Because this is a crazy part. We're not really good at Celsius temperature scales, are we? But we do know. So what's the freezing point of water in Celsius? 0. What's the freezing point of water in Fahrenheit? 32. So you know that 32 degrees Fahrenheit is equal to 0 degrees Celsius. We've been dealing with Fahrenheit our entire lives. What's the boiling point of water in Fahrenheit? Do we know? What's the boiling point of water in Celsius? 100. So even though we've been dealing with Fahrenheit our whole life, we still don't really know it that well because it's difficult and complicated, and the numbers are so random. So the boiling point of water in Fahrenheit is 212 and Celsius is 100. 0 and 100, easy. 32 and 212, Not as easy. The difference between freezing and boiling in Celsius is 100 degrees Celsius. In Fahrenheit, it's 180 degrees Fahrenheit. So that's why the Fahrenheit scale has smaller temperature degrees. So we're going to learn a few of them. I'm going to give you one, and that's 82 degrees Fahrenheit is 28 degrees Celsius. So it's probably not 32 degrees Celsius outside. It's 11 degrees Celsius. So, and the reason I tell you this to try to start to become a little more comfortable with Celsius temperature scales, because if you go on vacation to another country, they're going to look at you like you got three eyes if you start talking about Fahrenheit temperatures. Like people just don't know them very well. Has anybody ever been to a country where they don't know anything about Fahrenheit? But let's say you're in Australia and you say to them, oh, what's the temperature going to be outside today? I want to know how to dress. If they tell you it's going to be 32 degrees, don't grab your parka, because 32 degrees in Celsius is hot. So the reason we cannot use Celsius and Fahrenheit is, let's look at that. If temperature is measuring the speed of the molecules, and we just said all molecular motion can't stop on this planet, that would be absolute zero. We can't get there. We can't have negative temperatures. We can't have zero temperatures. Both Celsius and Fahrenheit have 0 degrees readings, which does not make sense. And that's why Kelvin is really the most descriptive and correct unit. Okay, do we know what heat is? We just talked about temperature being a measure of the speed of the molecules. Do you guys know what heat is? Let's start from the beginning. Is heat matter or energy? It is energy. So let's figure out what heat is. Everybody grab the leg of your desk. How does it feel? But how about the paper sitting in front of you? Does that feel as cold? Aren't they the same temperature though?
Yes.
They're both room temperature, aren't they? So that's what heat is. Heat is a flow of energy due to temperature differences. So why your desk feels colder than the paper in front of you is because you are touching metal, and metal is a good conductor of heat. So you're not feeling cold. Cold is only the absence of heat. There's really no such thing as cold. So what you're feeling is the heat energy leave your hand and enter the desk because your hand has more energy or a higher temperature. So heat is the flow of energy due to temperature differences. Which way does heat travel? You want to say up, don't you?
Down. Nice.
Let's think about it. Picture yourself, you're standing at the bottom of a mountain. It's about a nice 60-degree day. What's going to be on top of the mountain?
Snow.
Snow. Do you think it's hotter up there? It's not. So heat always travels from hot to cold. We measure it in joules or calories, and there's 4.184 joules in 1 calorie. We'll talk about way heat travels again in just a second. So everybody write down Formula 1. If we're dealing with temperature changes, our formula is going to be Q equals SM delta T. Q is heat, S is the specific heat capacity, and delta means change, and T is for temperature, so change in temperature. The S values are going to be different for various phases, so solid, liquid, gas are going to have different S values, and that's because the density is different. So our specific heat values for water is what we'll deal with first, are the amount of energy required to raise the temperature of 1 gram of substance, any substance, 1 degree Celsius. These are values that are going to be given to you. You do not need to memorize them. But notice that ice and water, gaseous water, so ice and water vapor, have lower specific heat capacities than liquid water. Liquid water is super happy. It holds a lot of heat. It is considered a good insulator. So the larger the value, the longer it takes to absorb heat and the longer it will keep the heat. The smaller the value, the faster it takes for the substance to absorb the heat, and it will keep it for shorter. So liquid water is high, metals are low. Let's talk about grabbing the leg of your desk. Again, heat is traveling from your hand into the desk. And if you want to keep yourself from being confused about the fact that heat does not travel up, heat always travels from hot to cold. Picture yourself grabbing the leg of your desk, which is underneath you. You know that in that condition, heat is traveling down. Well, now let's talk about if you go to your house, it's always coldest in the basement and hottest upstairs, isn't it? It's not because heat rises. It's because hot air rises. Why does hot air rise? It's less dense. And you're going to have a lot of people who are going to say to you, well, same thing. No, air is matter. Heat is energy. There couldn't be more different. And it's these little differences that are the cornerstone of a lot of scientific subjects. And this is the same thing with thermochemistry. If anybody decides they want to go into science and you want to study thermochemistry, there's going to be a lot of advancements that we need to make. Okay, I'm going to do a quick sample problem. We're not going to get deep into the math today in the Q equals SM delta T. When you notice that there's a starting and ending temperature, you know you're going to use the change in temperature formula. S is going to be my specific heat capacity. For water, it was 4.184. That's going to be given to you. Delta T means change in temperature. That's the mistake I see made most often. You got to subtract the ending temperature from the starting temperature. Notice my specific heat capacity is 4.184 joules per gram degree Celsius. That means the units of joules are on top. The units of grams and degrees Celsius are on the bottom. And then we'll plug in the mass and we'll plug in the change in temperature. And that will give us a unit of joules for our answer. 3 sig figs is what our answer will be in. This PowerPoint and these note sheets are in classroom already, so don't feel like you have to write everything down. Now let's convert that problem to calories. Remember, our conversion factor is there's 4.184 joules in 1 calorie. To cancel joules out, I'll put it on the bottom, and it goes with its 4.184. Still going to answer in 3 sig figs. We'll also have another formula. We're going to add all of these onto our heating curve in just a minute, but our next formula is H times N. Q equals H times N. It depends on the phase change you're dealing with. This is what we're going to use when we're going through a phase change and the temperature's not changing. These will also be given to you. You will not need to memorize this. So how much heat energy is required to change the temperature of 0.0598 kilograms of water to water at 0 degrees Celsius to ice at 0 degrees Celsius? So our formula becomes Q equals HM. When the temperature is not changing, you do not use the change in temperature formula. So all we're going to do is multiply those, but we also need to convert, remembering that our units in joules per gram tells us we got to have our mass in grams so that they cancel. There's 1,000 grams in a kilogram. If you remember that from first semester, great. You're going to need to use that. If you don't, I did record that. You can go back and through and check those out. So before we get to our heating and cooling curve, let's go over what this means. On a molecular level, when something's getting hotter, the molecules are moving faster. When something is getting colder, the molecules are moving slower. In order to increase the temperature, we will need to add heat to it, and that is going to make the molecules move faster. When we remove heat from a substance, it will get colder and the molecules will move slower. Heat always travels from hot to cold. So remember, heat is the transfer of energy due to temperature differences. And temperature is a measure of the average speed or average kinetic energies of the molecules. It's like a speedometer for the molecules. You need to understand the difference between heat and temperature. It's super important. So when somebody asks you, what is temperature measured? Don't say it's measuring the amount of heat. It's not. It's measuring the speed of the molecules. If two materials have the same temperature, they have the same average kinetic energy. So potential energy and kinetic energy are the two types of energy we're going to refer to here. Potential energy is stored in the position of the molecules or in the phase change of the molecules. That's going to be the plateaus on our graph. So all those P's are going to go together. Kinetic energy is the energy of motion, and it is the energy of temperature change. So let's go to our heating and cooling curve. You might want a couple different colors of pens or pencils, or just so we can separate. We're going to label a bunch of stuff on our blank heating and cooling curve that you picked up. So this is the heating curve for water. If you're going from left to right, you're adding heat. If you're going from right to left, you're removing heat. So that's why this can be called a heating and cooling curve. It is water, so the freezing point is at 0 degrees and the boiling point is at 100 degrees. So at 0 degrees, if you add heat to a solid at 0 degrees, you will melt it into a liquid. If you remove heat from a liquid at 0 degrees, you will freeze it into a solid. Now we'll go up to 100 degrees. If you have liquid water at 100 degrees and you add heat to it, you will boil it or vaporize it into a gas. If you have gaseous water or water vapor at 100 degrees Celsius and you remove heat from it, you will condense it into a liquid at 100 degrees. Notice during the phase change, the temperature does not change. So in the sections where the temperature is changing and the graph is slanted, you'll use the Q equals SM delta T. In the other ones, you'll use Q equals HM. The amount of heat you need to melt a solid is called the heat of fusion. The amount of heat you need to vaporize a liquid is called the heat of vaporization. Now, the reverse process is going to be the same quantity, but with a negative sign. So melting and vaporizing, you add heat to it, so it's endothermic. Condensing and solidification, you remove heat. The amount of heat you need to remove from a gas at 100 degrees Celsius to change it to a liquid at 100 degrees Celsius is called the heat of condensation. It's the same as the heat of vaporization, except it's negative. The amount of heat you need to remove from a liquid to change it to a solid is called the heat of crystallization. It is the same as the heat of fusion, but with a negative sign. You'll see it called heat of solidification or heat of crystallization. And the reason is because we have a couple different kinds of solids. We have crystalline solids. Most solids are crystalline, and we also have amorphous solids. So now let's add on there the sections that are slanted is delta KE, which means change in kinetic energy or change in temperature. The flat plateau parts are change in potential energy or position of the molecules. So on the plateau or the flat parts, we are not changing the temperature, we're changing the arrangement of the molecules or the potential energy. So in sections A, C, and E, we're changing the kinetic energy. In sections B and D, we're changing the potential energy. So remember the 3 P's. At the plateaus, during the phase change, we're changing the potential energy. So on the slanted parts, you're going to use Q equals SM delta T. On the flat plateau parts, you're going to use Q equals MH. So each section has its own constant. So the S or H values have one section of the graph that they're going to use in. Never use the same constant for 2 sections of the graph. These are individual to the individual parts. And the formula will be a little different also. So anytime we're going from left to right, we are adding heat, and that will be called endothermic. So those phase changes and temperature changes are endothermic when we're going from left to right and we're adding heat. When we're going from right to left, we're removing heat. Those are called exothermic. So temperature changes are a change in kinetic energy. We'll use different heat capacities depending on the state of matter, and our formula will be Q equals Sm delta T. Heat capacity is the energy required to raise 1 gram of a substance by 1 degree Celsius. During a phase change, we're changing the potential energy, temperature remains constant, and our formula becomes Q equals HM.